Hi, I'm Julie Yu, Senior Scientist at the Exploratorium, and I'm lucky to be in conversation today with Dr. Nikki Fox, who is the Director of the Heliophysics Division at NASA. And the Exploratorium and NASA have had a long time collaboration in bringing images of the total solar eclipses that happen around the world to the public. And so I wanted to start off today by asking you, Nikki, have you ever experienced a total solar eclipse? And what was it like, if so?
I have actually. I just the one that was in the US in 2017, the eclipse across America, and it was an amazing experience. It was kind of an interesting thing. I was there during the day, and the sun was shining. It was all beautiful, and I had actually had my parents fly over from England. I took my children. I took several of my really close friends, and we went to Beatrice in Nebraska, which was one of the sites for the NASA broadcast. And so I was there, and I'd been there for 2 days. Fantastic weather, and of course the moon is going, kind of taking those bites out of the sun, and the clouds rolled in, and the sun disappeared. And so my dad just looked at me and said, "It's going to clear up, right?" And at that point, I realized, wow, I have dragged all these people and I've put them in a field in the middle of nowhere in Nebraska, and we're not actually going to see this eclipse. Then, to make it worse, it started to rain, and so I go over to do the live broadcast for NASA, and I'm really depressed because I'm not seeing anything, but I'm trying to put on a good front. I'm talking about Parker's solar probe and how close it will get to the sun, and where in the corona you would be able to see it. And then I see the shadow sort of streaming towards us of the sort of approaching eclipse. And so I'm talking about it getting dark and various other things. And while I'm talking, they're telling me you need to turn around because I had my back to the eclipse. So I turned around, and the clouds had just cleared to sort of almost frame totality. There was just this gap in the clouds where you could see totality. And it was such an incredible experience because not only was the eclipse mind blowing and beautiful, and I'm starting to tear up even talking about it, but it was just so, so emotional. But to have this sort of almost clearing as I turned around, it was sort of a spiritual thing. And I said afterwards, I didn't know whether it was maybe that God wanted me to see a total eclipse, or whether God just didn't want my dad to complain to me for the rest of his life about missing this and sitting in a field. So it was just incredible. And I remember sort of saying, wow, just look at that corona. Just I've studied the corona, or I've studied the sun, but to see it and just really say, okay, that it really is there. That's what it looks like. And then, as the diamond ring came out, and oh my goodness, it was just amazing.
We've learned that luck is a critical component in being able to image these eclipses. I think it's pretty special to have had this emotional experience with something you've studied professionally your whole life. So, how did you get into studying the sun?
I sort of wandered into it. I mean, I've always been interested in space. I've always loved science, but always been really interested in space. And so I did a PhD in space plasma physics at when I was in London at Imperial College, and just really loved all of the aspects. But there, I was focusing much more on the Earth's magnetosphere, so the protective bubble that we have that protects us from the solar wind and a lot of the solar radiation, and sort of the study of that and how it couples to lower levels, so how it couples to the ionosphere, and how the aurora form. And so that was kind of where I came in. But then I was super lucky. I got offered a postdoc position at NASA's Goddard Space Flight Center. So I moved there, and I worked there for a few years, and then went up to the Applied Physics Lab. And there I started working on the Van Allen probes. And so I expanded from looking at the aurora to really looking at the radiation belts too. And so that was really fascinating. And I spent a couple of years really looking at radiation belt dynamics. And then I got this amazing opportunity to be the project scientist for Parker's solar probe. And then that's when I really started studying the sun and studying the corona. Before that, it was really more the sun was the starting point to the energy flow that was going to cause the phenomena inside the magnetosphere. So the sun was really a cause for me for a while, and then I started actually studying it, and then you get this really holistic view of space weather and the importance of studying our star and knowing what is coming towards us and how that's going to impact our planet. So I've kind of piecemeal built up the whole space weather discipline, now studying the sun in great detail. And then, actually, right before I started at NASA headquarters, I was working on a mission called IMAP, which is studying the very opposite of the sun. It's studying the very edge of the sun's influence. And so the solar wind, the atmosphere that you see, the corona that you see during the total solar eclipse, is continually heated and accelerated. And so it moves away from the sun. It bathes all of the planets, and it actually kind of carves out a protective bubble for our solar system as we are orbiting around the Milky Way. The solar wind actually creates this cavity, and that protects us from a lot of nasty stuff that's out in interstellar space. So I've kind of studied every possible aspect of the sun, both the sun itself, but also its impact on our planet, and then all the way to the very edge of the solar system.
That's amazing. And now you're the director of the heliophysics division at NASA. And so for folks who may not be familiar with that term, can you just go to straight basics? Like, what is the division of heliophysics interested in understanding?
So we are interested in understanding everything about the sun, from the solar interior all the way out to the corona, and then how, in turn, that star impacts not just Earth. We're very, very interested in Earth. Obviously, it's our planet. We really want to understand space weather impacts that can affect our technology. But it's more than that. It's really the sun's influence on all of the planets and all the way out to how it creates this heliosphere. So heliophysics is really the study of the sun and everything that the sun kind of causes or drives for us. And if I'm talking to school kids, I always say I'm kind of like the Lion King. I control everything the light touches. So everything the sun influences is heliophysics.
And so, thinking about those kids, can you give an example of something that we're studying right now that kids could relate to that like impacts their everyday lives?
Absolutely. So we rely on technology. We absolutely rely on technology. I mean, if you think about it, when is the last time any of us ever looked at a map? We just plug it into our phone and we expect that the voice in our phone is going to guide us to wherever we want to go. So imagine if you lost that ability. So the sun actually impacts various different places in our sort of protective bubble that we have around Earth. The aurora, if you see beautiful aurora overhead, that is actually a big current system in the sky, and that can cause problems for power grids. If you lose power, you can't actually charge your devices. Also, we now know there's a big interaction between terrestrial weather, so storms that we see down here on Earth, um, kind of where the terrestrial weather stops and space weather starts. There's a boundary there, and they actually interact. Those two weather systems interact, and sometimes we see things like bubbles of material, so bubbles of plasma that form in this region that actually can impact signals that need to go through it. They can be absorbed, they can be reflected, they can just get garbled, and so that actually will impact our ability to do navigation. So that will impact GPS. So there's a couple of things. When I talk about some of the big events, the Carrington event that happened in 1859, and I say, the telegraph system went down in the US for 4 days. And I look at the kids and I can see them thinking, telegraph system, I don't know what that is, and B, oh well. And then I say, just imagine that you lost your internet for, your Wi-Fi goes down for 4 days, and then it really gets into perspective that's we rely on things differently, we use technology differently, and we are way more susceptible to impacts from the sun.
Yeah, right. So we have the division of heliophysics to thank to allow us to keep texting, I guess, every day. I understand that you have basically a whole fleet of spacecraft up in space helping to study these things. So can you talk about what are some of the things that those folks are looking for?
Yes, you're right. We do have this wonderful fleet, and it's very strategic. We think about what is the science we want to do and where is the right location to do that science. And so we have missions that go all the way from very close to the sun. Parker Solar Probe is the first mission to really go and fly through the sun's corona. So that beautiful area that you see every time you watch a total solar eclipse, Parker Solar Probe is kind of in that region, going through that tenuous plasma, that coronal material or the solar material that you see illuminated during the eclipse. So we have the spacecraft that are very close to the sun. We have lots of spacecraft that kind of look at the sun in different wavelengths. One of the things you learn is you need to look at things from a lot of different perspectives. So if you imagine if you could only see, if you were looking at a flower, but you could only see the green, all you would see is the stem. So
Yeah.
you wouldn't be able to see the petals. So you wouldn't understand anything about the reproductive cycle of a flower. You wouldn't be able to see the roots because you couldn't see brown. And so you wouldn't understand how it feeds and how it gets its nutrients. You'd only see like this green stem. And so when we look at the sun, we need to look at that full range, not just all of the different kind of colors in there, but ultraviolet, infrared, they all tell us different pieces of a puzzle. And so we look at the sun in all different wavelengths. We look at, the sun is very noisy. It has radio signals, it has microwaves, it has infrared. Every single piece of that we want to look at to really help us to understand our star. We have spacecraft that sit between the sun and the earth. They're kind of like our early warning system, a bit like buoys in the ocean. They tell us what is coming towards us. So, like a windsock in an airport, which way is the wind blowing, which way is the magnetic field pointing as it's coming to us here at Earth. Of course, we have wonderful spacecraft in all the key locations around Earth, in the magnetosphere, and then also much closer to the surface, going through the ionosphere and the lower regions of our atmosphere. So they are really giving us that Sun-Earth perspective. And then we have missions, I mentioned IMAP, that will launch in a few years. That is going to be imaging the kind of fragile boundary between where the sun's influence stops and interstellar space starts. And we have our Voyager spacecraft that have been going more than 40 years. They originally were planetary missions. They did flybys of the planets, but because they kept on going, they've actually crossed through that tenuous boundary and they're out in interstellar space. So they're not even anymore in the region of our sun. That's just some of them. And of course, we have lots of missions in between, but they're the key locations that we want to go to be able to do our science.
Yeah, that's amazing to have all of these pieces, like kind of piecing together all the components to give us a broader picture. So I guess my last question for you is, since you're aware of all of these missions and kind of where they are in terms of their explorations, is there anything that you're excited about that we can kind of anticipate hearing about soon in the future, like some discovery that we're looking forward to?
Well, I have to say, we're watching Parker Solar Probe. Parker Solar Probe uses gravity assists of the planet Venus to actually kind of shrink the orbit. So Parker is getting closer and closer to the sun. And so it's almost like a brand new gift each time we do a Venus flyby because we're in a whole new region of the corona. And so as we get closer, there are some things that we've seen, some features that we saw early in the mission on the very first orbit in 2018. And we saw some little features, and we think these features are really associated with mysteries like why is this corona? It's 300 times hotter than the surface of the sun. And that doesn't make sense. If you walk away from a heat source, you wouldn't normally get hotter. So we want to understand why do we suddenly see that increase in temperature, and why is it suddenly accelerated there so much so that it can break away from the pull of that giant star and move all the way out, bathing all of the planets. So those mysteries, we've seen some little features, but as we get closer, we're seeing those features getting much more prominent. They're getting bigger. They're giving much more of a punch, and they're getting more frequent. And so we think we're really moving in on why we see this coronal heating. Also, just learning more about our star because it's very important to us. It's our sun. It's why we're here, but it is also just kind of an average star. And so what we learn about our sun, we can apply to other stars in other stellar systems. So I would be looking out very much for continued great results from Parker Solar Probe, helping to really unlock the mystery. It's kind of that missing piece. We know a lot about the interior of the sun. We understand what happens as the solar wind comes close to our planet, but what is happening in that mystery region? And Parker Solar Probe's flying right through that mystery region right now.
That's really fantastic. Super exciting. So, Nikki, I really want to thank you for your time and all of your work in helping us learn more about our star and what's going on in heliophysics at NASA.
Oh, you're welcome.
And
It's a great job to have. It's a great thing to study. You're always surprised, always challenged, and our star throws us something new every day. So I have to say, I think I'm probably the luckiest girl in the world with my job.
great. Thank you so much.
Thank
And
you.
for those of you watching, if you want to learn more about the Parker Solar Probe, stay tuned for our next conversation with Eric Christian from NASA and Desiree Whitmore from the Exploratorium.
Hola, my name is Dr. Desiree Whitmore, and I'm a physics educator here in the Teacher Institute. And I'm here today with our friend and collaborator from NASA, Dr. Eric Christian. Welcome, Dr. Christian.
Thank you, Desiree. Yeah, I'm, as she said, Dr. Eric Christian. I'm a researcher with NASA, have been for a number of years, and my specialty is heliophysics, which is the study of the sun and all of its effects on the solar system. My main interest is actually in building instruments, then getting the data from those instruments and doing great science with them.
Wow. Okay. So, what actually originally got you interested in science?
So I've actually wanted to work for NASA since I was about 8 years old. The Apollo landings. By that time I was 8, I knew I was good at math and science, found it exciting, and so just naturally fell into, you know, a science career, work doing the college work that I needed to get a degree in physics and then a PhD in astrophysics, and then immediately started working for NASA after getting my doctorate.
Wow, so it's like a dream come true. Like you're a child and you're like, I love NASA and I want to do space stuff. And then you actually did all of the things and are doing space stuff now.
Yep. Well, I always joke that I wanted a job that paid me to have fun. And working for NASA can be a tremendous amount of fun.
Yeah, that's really awesome. And so now you're working, you were originally interested because of space shuttles, right? And the Apollo missions, but now you're working studying the actual sun. So what does your mission, the Parker Solar Probe, what does that actually study about the sun?
So, Parker Solar Probe is our first mission to the sun. We're actually going to, over the next 5 years, get closer and closer to the sun. And the way we do that is using Venus's gravity to move ourselves closer to the sun. We're going to get within 4 million miles of the surface of the sun. That's 25 times closer than the Earth is. And the important thing is that there are things we can't measure from Earth or from anywhere spacecraft in Earth orbit. We're 93 million miles away from the sun, and a lot has happened to the solar wind and the solar energetic particles that we're studying in that 93 million miles. By getting down to 4 million miles, we get to where the action actually is happening. And then we can really understand the sun for the first time. This is something we've wanted to do since the beginning of NASA. It was actually one of the first missions proposed, but we haven't had the technology to do it until recently.
Wow. Okay. That's really exciting. So then another question I have is you launched this probe 93 million miles. How big is it?
It's about
Exactly.
the size of a small bus. It's a pretty big spacecraft. A lot of it is a big heat shield in the front of the spacecraft to protect us from the sun. My instrument and most of the electronics hides in the shadows behind this heat shield because the sun is at 4 million miles is hot enough to melt aluminum. The heat shield is the new technology that really allowed us to do it. It's this special carbon foam with a carbon composite front and back. They spent a lot of years and a lot of money developing this heat shield before they even started the rest of the spacecraft because without it, we couldn't do it.
Wow. Well, then actually, I'm wondering if it's that close and it's orbiting, it must be going really fast to get around the sun, right? During its orbit. So how fast is it actually going to travel at its fastest approach or its closest approach?
That's right, because big objects which have a gravity well, it's sort of like rolling down a hill. And at the bottom, you're moving faster than you are at the top of the hill, which is the far end of the orbit. So when we get to our closest approach at 4 million miles, we're going to be moving at 200 kilometers a second or half a million miles an hour.
That's
The,
crazy.
the fastest human-made object of this size ever.
Wow. I was trying to think about this because I'm like 200 kilometers. The speed limit is roughly 100 kilometers per hour. So that means it would take me 2 hours to drive to a place where this probe could get to in 1 second.
That's right.
As it's spinning around the sun. Like, that's
Yeah.
pretty fantastic.
Mm-hmm.
So what kind of data are you actually collecting? You mentioned that you're studying the atmosphere of the sun and the solar wind. And what kind of data are we actually collecting from that?
So there are a number of different instruments on Parker Solar Probe. There are actually a pair of cameras that look off to the side because you can't look directly at the sun when you're that close. They're just like things that you may have seen called coronagraphs that look at the corona of the sun, which is the part you see during a total solar eclipse. But it does it by looking off to the side, and you don't have the atmosphere to worry about. So, two cameras that look at the corona off to the side. There are electric and magnetic field measurements because the sun's solar wind carries magnetic field out with it. And so in order to understand all of the physics of what's going on, you need to measure the electric and magnetic fields. And then there's a couple instruments that measure particles. These are the solar wind. These are pieces of atoms, electrons, protons, heavier nuclei of atoms that are moving at anywhere from 1 million miles an hour for the solar wind up to almost the speed of light for things called solar energetic particles, which are the things that I measure. And so these collect these very high speed particles, and using various specialized detectors, not light, but using specialized detectors, they can actually figure out what particles are moving through them.
Wow. So two things you mentioned that I'm very curious about. One is, can you explain more about what the solar corona is
Mhm.
and why we can only see it during eclipses?
The solar corona is the atmosphere of the sun, and it is much less dense than the sun is. The sun is not a solid. It actually moves like a liquid, which makes some things really weird because the equator is spinning faster than the poles are, unlike on Earth, which moves as a solid body. So the sun is more like a liquid, but it's a lot denser than the atmosphere, which is the corona. That corona is also the solar wind. It's the particles streaming out from the sun. And that atmosphere actually extends way out beyond the orbit of Pluto. The sun's solar wind has blown a bubble in interstellar space. And the two Voyager spacecraft have only in the last 5 years gotten outside of that bubble and into interstellar space for the first time ever. But that's more than 10 billion miles away from the sun. So we live in the atmosphere, not only the atmosphere of the Earth, but the Earth sits in the atmosphere of the sun, as do all the planets.
So actually, you mentioned that you are particularly measuring high energy particles that are coming off of the sun in the solar wind. And I'm wondering, normally when you hear about scientists who are running a certain project at NASA or any other organization, they're kind of in charge. They didn't build the instrument. They didn't design the instrument. So I'm wondering, did you have anything to do with the design and construction of this probe before it was launched?
So I am one of the leaders of one of the 4 instrument suites on Parker Solar Probe, but the scientists tend to build the instruments and study the data from the instruments. And there's a big team of really capable engineers who design and build the spacecraft. We work hand in hand with them because they need to know the requirements on the spacecraft in order to get the science done. But the actual design and construction of big, expensive spacecraft like this are done by a team of engineers.
All of this thought and work went into this instrument. And so now it's been out orbiting the sun for 2 years. What have we learned so far?
So we're only just now sort of touching the surface of what we're going to learn. We're still trying to figure it out. A lot of what we've seen we don't understand. And that's the fun part, because now we're trying to figure out, and as we get more and more data, the sun's been very quiet until just about a couple weeks ago. For 2 years, the sun has been in its solar minimum state, where there aren't very many of the big solar storms that can cause space weather, what are called coronal mass ejections and solar flares. As we've gotten close to the sun, and we haven't gotten as close as we will in 2024, but as we've gotten close to the sun, we find that the magnetic field that we knew was there has a lot more funny wiggles that we never saw. And that's, I think, a clue, because we think it's the magnetic energy that's going into heating the solar wind and the corona and accelerating the solar wind. So we're starting to see things close to the sun that we don't see regularly out at Earth orbit. And that's the clue that we're getting down to where the action is. And I think that's part of the fun part. This is something that we're going to be studying for many years. When we completely figure out the Parker Solar Probe data, we're probably going to need to launch another probe close to the sun to figure out the questions that came out of the Parker Solar Probe data. So science is this amazing journey where you find an answer to one thing, and that just leads to more questions. It's like doing a giant jigsaw puzzle that is the universe, and you find where one piece is, and that just gives you a clue as to what the next couple pieces look like. And so a scientist then goes to look for those. So this is fun.
Yeah, awesome. Actually, that makes me think about the fact that after our interview, we're going to be speaking with another scientist about space weather. And your Parker Solar Probe is finding a little piece about space weather that this whole other probe is now going to go and learn about.
Yep. So it's all connected.
It's all connected. Well, thank you so much, Dr. Christian. It's been a pleasure. And I can't wait to learn more about all of the awesome things that Parker Solar Probe are doing.
Thanks.
Hola, soy Isabel Hawkins, astrónoma del Exploratorium, y hoy tengo mi colega Yari Collado Vega, una doctora en astrofísica espacial de la NASA, quien nos acompaña. Bienvenida, Yari, ¿cómo estás?
Estoy bien, Isabel, muchas gracias por esta invitación. Estoy muy contenta de estar aquí con todos ustedes.
Qué bueno, mira, yo realmente me admira tu trabajo y tengo entendido de que tu especialidad es la meteorología espacial. ¿Por qué no nos cuentas un poco de qué se trata?
La meteorología espacial es el estudio de las condiciones en el espacio que son mayormente dominadas por la actividad solar. En el Sol, en la corona solar, que es la atmósfera solar, se generan estas tormentas solares que aquí en la Tierra pueden causar problemas con los instrumentos de los satélites en el espacio, problemas con los sistemas de comunicación, los sistemas de GPS, y también pueden causar problemas en las redes eléctricas. Nosotros pues estudiamos cómo esto ocurre y también cómo podemos pronosticar, hacer esos pronósticos para poder proteger las misiones en el espacio.
Sí, pero realmente lo interesante es de que estamos nosotros bañados de lo que llamamos el viento solar. Pero el viento solar se diferencia a los vientos normales que nosotros aquí percibimos sobre la Tierra. ¿Cuál es la diferencia esencial del viento solar a un viento común, digamos, de aquí en la superficie terrestre?
El viento solar como tal nos cubre todo el sistema solar, ¿okay? Y llega hasta una denominación que es lo que nosotros llamamos la heliosfera. Y simplemente es la expansión de esa corona solar, de esa atmósfera del Sol hacia lo que nosotros llamamos entonces esa heliosfera. Y mi campo es el estudio de la heliofísica, que estudia cómo el viento solar interactúa con todos los cuerpos en el espacio y también con las diferentes misiones que se encuentran a través del sistema solar.
Fíjate qué interesante, o sea, has hablado tú de cómo esas partículas cargadas del viento solar tienen su interacción con los GPS, con las redes de electricidad, pueden afectar a los astronautas en el espacio, o sea, ese pronóstico que tú haces es muy importante de esa meteorología y tengo entendido que tú trabajas en un centro de la NASA ya por 17 años, o sea, eres parte de la familia de la NASA. ¿Y en qué consiste tu trabajo en sí?
Yo soy la líder del grupo de meteorología espacial para el Centro de Modelaje Comunitario, o CCMC por sus siglas en inglés, en NASA Goddard. Lo que nosotros hacemos son los pronósticos de esas tormentas solares para ver dónde y cuándo van a llegar a las diferentes misiones de NASA para proteger a las misiones. También actualmente estamos trabajando con el equipo de NASA Johnson para entonces hacer pronósticos que protejan a los astronautas que próximamente llegarán a la Luna y luego en un futuro hacia Marte.
Fíjate, y claro, y cuando están viajando los astronautas a través del espacio, hay veces que el Sol emana, por ejemplo, una gran cantidad, miles de millones de toneladas de partículas cargadas que se llaman reacciones de masa coronal. Entonces, ese tipo de fenómeno es particularmente peligroso para los astronautas, tengo entendido. ¿Cómo haces tú para predecir ese tipo de evento?
Lo que realmente es peligroso para los astronautas es lo que ocurre cuando ocurre una CME, que es la eyección de masa coronal por las siglas en inglés. Cuando la CME ocurre, hay una aceleración de partículas de altas energías y la aceleración es en fracciones de la velocidad de la luz. Partículas altamente cargadas que viajan a altas velocidades y esas son las partículas que pueden crear un nivel de radiación que es peligroso para los astronautas. Nosotros entonces estamos tratando de conseguir y validar todos esos modelos que se encuentran actualmente en el campo que pueden predecir esas partículas, cuándo ocurren, cuánto es la intensidad y cuánto va a durar el evento. Entonces, nosotros lo que hacemos esos análisis y entonces podemos comunicar esos análisis al centro de control que a la misma vez comunica eso a los astronautas para saber si se tienen que entonces proteger de esos eventos.
Claro, y supongo que es particularmente esencial que ellos se puedan proteger si están trabajando fuera de la estación espacial o de la nave, ¿no es cierto? A veces que se van afuera a hacer alguna corrección o algún arreglo de algún instrumento y entonces seguramente ahí es el momento más clave.
Exactamente, el pronóstico no es solamente saber que está ocurriendo un evento, es si podemos predecir si va a ocurrir, porque entonces de ahí ellos hacen sus planes de si pueden ir afuera a hacer las actividades que tienen que ir a hacer. Y esto es algo que estamos planificando ahora mismo y es algo que a mí me alegra mucho que pueda ser parte de estas actividades de exploración humana en la NASA, porque es algo que nunca pensé que podría llegar a ser y ahora voy a ser la directora del grupo que va a ayudar a estos astronautas a estar a salvo en el espacio.
Qué fantástico. Mira, sí, realmente, o sea, tú eres muy joven, pero ya tienes 17 años de ser parte de la familia de la NASA. Y me imagino que cuando tú creciste ahí en Ponce, Puerto Rico, una niña corriendo a las afueras, no sé, ¿cómo te inspiraste para realmente llegar a esta posición tan importante que tienes ahora?
Mi historia es bien interesante. Yo vengo de una familia bien humilde de Ponce, Puerto Rico. Y mis padres lograron reunir dinero para ir a Florida cuando yo tenía 6 años, a celebrar el quinceañero de mi hermana. Y además de ir a Disney, porque todo el mundo quiere ir a Disney World, también fuimos, mi padre sabía mi interés por la ciencia y nos llevaron entonces al Centro Espacial de Kennedy. Y ahí entonces yo empecé a ver todas estas cosas del espacio, el programa de transbordador, todas estas cosas y me enamoré. Y ahí yo tenía 6 años y fue la primera vez que yo dije que yo quería trabajar para la NASA. Pero luego cuando uno crece, una vez se desvía un poco y cuando empecé cuando estaba ya en la secundaria, comencé entonces a pensar que quería estudiar turismo y hasta leyes. Pero tenía una maestra bien buena de ciencias que me decía, no, tú a mí me dijiste desde hace mucho tiempo que querías estudiar ciencia y física es lo que te gusta. Entonces ahí cogí y entré al departamento de física de la Universidad de Puerto Rico de Mayagüez y no te puedo negar que hubo un momento que hasta me quise cambiar de la física, porque la física no es fácil.
Claro.
Y también me gustaba mucho la ingeniería eléctrica, pero entonces luego me encuentro a otro mentor que era mi profesor de física, que siempre lo recuerdo con mucho cariño, y él no me dejó cambiarme de departamento. Y me dijo, tú vas a entender lo que es la física, yo entiendo y veo en ti la capacidad de ser una buena científica. Y mira dónde estoy. Luego, él mismo me sugirió hacer internados de verano y comencé a hacer internados de verano siempre aplicando a la NASA, pero la primera vez no entré, ni la segunda tampoco. Los primeros 2 internados de verano los hice aquí en Maryland, en otra organización, y entonces la tercera vez, ahí fue que me aceptaron, y ahí fue que entonces entré al internado de verano en la NASA hace 17 años atrás, y el tiempo de verdad que parece que vuela.
Que vuela. Entonces creo que una de las enseñanzas clave de lo que nos cuentas es realmente la perseverancia y el papel tan importante que juegan nuestros mentores, ya sean nuestras familias, nuestros maestros. Qué bonito que tú los recuerdas con tanto cariño, son personas que realmente han tenido una influencia especial en tu vida. Y yo me acuerdo que cuando yo era chica también me inspiré a través de las estrellas, a través del sol, de los eclipses, ya sea lunares o solares. A veces solo veía un eclipse parcial, pero hay veces que tenemos la suerte de ver un eclipse solar total, donde se ve esa corona que has estado mencionando. Entonces, ¿cómo es que ustedes utilizan la corona solar, sobre todo durante los eclipses, para poder entender más sobre lo que es el clima espacial o las tormentas espaciales?
Cuando nosotros tenemos un eclipse total solar, nosotros tenemos la capacidad de ver partes de la corona que usualmente no vemos. Los científicos hacemos eclipses artificiales todo el tiempo para poder ver para dónde se dirigen esas eyecciones de masa coronal. Si no, no se podrían ver porque el sol es bien brillante. Y la única manera de ver esas eyecciones de masa coronal y hacia dónde se dirigen es tapando el sol. Nosotros lo hacemos de una manera artificial con lo que llamamos un coronógrafo. Este instrumento es tremendo, pero por la distancia que nos encontramos con el Sol y la Tierra y donde se encuentra el instrumento, a veces tapamos más de esa corona solar que queremos ver, en verdad. Entonces, cuando la luna tapa el sol de una manera casi perfecta, estamos viendo partes de la corona que usualmente no podemos ver. Y entonces ahí los científicos analizamos esas partes de adentro de esa corona donde es que se originan estas tormentas solares y utilizamos entonces esas observaciones para validar los modelos para hacer mejores pronósticos en un futuro de la meteorología espacial.
Qué fantástico. Entonces, realmente el papel que juega un eclipse solar total visto desde la Tierra es todavía muy importante y se puede compaginar con estas observaciones desde el espacio que ustedes hacen con estos satélites de la NASA. Qué fantástico, realmente. ¿Y tú has visto un eclipse solar total? ¿Has tenido esa experiencia?
De verdad que afortunadamente he tenido 2 experiencias. La primera fue estaba en Carolina del Sur, trabajando con el equipo de la NASA en el show que tenían en vivo. Y desafortunadamente esa vez estaba nublado y no pudimos ver el eclipse como tal, pero sí se pudo observar que se oscurecía y a la misma vez que bajaba la temperatura, y eso fue algo impresionante. Luego entonces en el 2019 tuve la oportunidad de viajar a Argentina y ahí sí, ahí vimos el eclipse total solar y yo no hay manera para yo explicar cómo eso se siente, pero ya yo entiendo por qué hay personas que ellos todo el tiempo quieren ir a ver un eclipse total solar y ellos se encargan de ver todos los que puedan ver. Y es porque es un evento tan impresionante. Tú con tus propios ojos estás viendo la corona solar y es como si de verdad te transportaras hacia el espacio y pudieras ver entonces esa es lo que nosotros le llamamos los streamers, que son las partes estas del campo magnético que salen de las regiones activas. Y tú lo ves con tus propios ojos y es algo impresionante. Y no solo eso, cuando se oscurece, baja la temperatura, los animales cambian su comportamiento. Es verdad impresionante y se lo recomiendo a todo el mundo que deben de verdad alguna vez en su vida, aunque sea una sola vez, ir a un eclipse total solar.
Así es, como yo siempre les digo a los videntes de nuestros videos, de nuestros programas, 99% no es igual al 100%. Hagan el esfuerzo de entrar a la franja de totalidad para tener esa experiencia. Y yo realmente comparto contigo esta emoción de ver un eclipse solar total. Y cuando lo vi por la primera vez, mi primera vez fue en Turquía en el año 2006, yo realmente tenía lágrimas en mis ojos, estaba muy emocionada y me sentí por primera vez que somos parte de un sistema solar en dinamismo. Se veían los astros moviéndose, interactuando. Qué bonito, realmente. Bueno, muchísimas gracias, Yari, por toda esta excelente conversación. Te deseo lo mejor para tu carrera, para tu futuro, y que sigas realmente aportando de tu gran inteligencia para poder entender mejor lo que es la meteorología espacial. Muchísimas gracias.
Gracias, Isabel. Gracias por esta invitación. Chao.
Chao.